Okay, thank you. So what I'm going to be talking about is, I guess, sort of like ongoing projects come obsessions I've been working on for many, many years now. I mean, this stuff actually goes back for me probably about 30 years to when I was originally an undergraduate and read basically Darcy Thompson's book on growth and form, and that's probably sort of infected me to sort of like carry on obsessing about things for many, many years. What I'm going to be focusing on is some work from the last 5 years, which basically has been looking at how to create complex sculptural forms based on growth rules. So I'm not trying to copy biology. What I'm trying to look at is almost like if you have almost like an abstract process of growth, what sort of things could be created by that? And almost like exploring that space of possibility to find out almost like, what are the unexpected things that can come from that? So I guess it's almost like sort of driven by almost like seeing the sorts of things you see in nature, and it's almost like the range of almost like emotional response that I think you get to things in nature. I think it was like some of the most almost like sublimely beautiful, but also through to the most like complexly ugly, almost like revolting things. I think there's the thing about natural grown form that has this deep, almost like psychological, emotional sort of response. And it's almost like abstracting it to see almost like if we're actually creating things by very artificial rules for growth in a computer, not trying to emulate specific things in biology, but just basically using the computer to simulate growing things in a very abstract way. Almost like how interesting, complex, and maybe emotional things can that produce as well. So to start, I'm just going to start by showing a video so just to explain a bit more what I'm talking about. So let's sound down probably a little bit. So basically what we're seeing here is some work from a video I produced a couple of years ago called Cellular Forms. And basically what you've got is a number of structures that all start with the same ball of cells. So basically you're going to see a number of different animations, and it all starts with the same ball of just 42 cells. And then they're just like very slightly different rules for those balls for how it then progresses. So basically they're rules for how cells divide, when cells divide. Cells basically usually accumulate food, and when they get enough food, they're then selected for dividing. And when they divide, it's on things like which direction do they split in? How do they reconnect the cells that are around them? What forces do they exert on the cells around them? So it's basically, the cells interact with the cells immediately around them. They don't have any global things. It's just almost like very, very local behavior happening between the cells. And then just by slightly changing these rules for either the system or just like forces and the parameters between the cells, it's like maybe like if there's a slightly more force between the cell, what happens? If it maybe splits more in the direction of maximum stress on the surface, what happens? Hopefully what you start getting is often very, very, very different sort of structures sort of coming up, which may range from things like maybe like coral-like, folded skin-like, quite a lot of different structures. So it's basically what I'm going to try to do is like come up with these hopefully very, very simple rules. I mean, I say I'm not a biologist. I've actually come from a maths background originally. And I'm much more interested in, almost like come up with a system which is actually very, very unbiological. Actually, we quite like that. But even though it's it's a growth system but extremely unlike biology, does it still produce familiar things you see? And it's almost that sort of alien and familiar that hopefully it's going to produce. I'm not going to produce things like maybe exactly like an oak tree or exactly like a frog embryo or something like that. But hopefully it's going to produce things which are maybe deeply reminiscent and maybe in strange combinations of things that you actually see in nature. So it's almost like I'm deliberately trying to create alien to hopefully evoke the familiar. And then what I'm also doing is I am, I guess, actively intervening in this, I guess, almost like as an artist. So the simulations themselves, I almost like don't touch. It's almost just like you sort of set the parameters, set the blue touch paper, let it go. I don't actually intervene in the simulation. I just see what it does. So it's almost just like growing a seed and seeing what it grows into. But I'm very actively intervening in almost like choosing which seeds to grow. So I'm things like growing lots and lots of things to the seedling level, effectively, and then seeing which things look to me like things that got potential that I want to explore further, and then sort of things like maybe crossbreeding and mutating those seedlings, or exploring, especially when I say explore the space of possibilities, these seedlings. And to be honest, most of the time it just produces junk. I mean, what you're seeing sort of here are, it's the cream of the cream. Mostly what it produces when you just almost like you just randomly set these parameters, you're just going to get, at best, probably a twitching ball of jelly, or something that just sits there and does almost nothing. But there are just very, very few places in almost this space of possibilities of, the parameters for these creatures almost, where suddenly it starts doing interesting things. So that's another thing I'm really interested in. It's almost like, creating almost like badly behaved system, which most places it's just going to do really, really uninteresting things, but a few places hopefully does remarkably. So it's almost like evolution by survival of what I find intriguing. So a lot of what we're doing is almost like writing software, as well as doing simulations and rendering things, but also for how I explore that space. How do I find if I find something interesting, how do I try to exploit it? How do I refine that? And how do I find new areas where maybe there's something else that I've never seen before sort of happens? So how do I sort of explore that space? So, okay, so we've got quite a short talk today. I'm just going to very briefly talk about some of the main influences. And I'm afraid this is probably almost like the most unoriginal trio of influences for this type of work, but it's genuine. These are three people whose work I just go back to again and again and really sort of inspired, what I do in really fundamental ways. Firstly, sort of Alan Turing, obviously amazingly well known for so many things, helping save our country during the Second World War, but also, basically being one of the main fathers of computing. And probably, I guess, all of you know, one of the last things he did was think about how the sorts of patterns you see in animals and things in nature, the things that come, the patterns of morphogenesis, how could those potentially be created by very, very simple mathematical systems of just things like pairs of chemicals reacting with each other, diffusing one cell to another and reacting with each other. And basically seeing that you can produce, hopefully all the sorts of things you see, like, spots and stripes and like intricate structures of spots within spots and things like that in nature. And it's basically the idea of a very, very, very simple mathematical rule, particularly a system that feeds back in itself, can produce an incredible range of rich variety. So basically what's called reaction diffusion equations, in this paper he wrote called The Chemical Basis of Morphogenesis. Next is Darcy Thompson, who, his book on growth and form, which I guess it's almost coming up to 100 years. It's written originally in 1917, so next year is going to be the 100 years since growth and form was written. And probably this is the biggest thing that set me off. Reading this when I was an undergraduate, so I just saw it was published in the bookshop. We republished prints of great, works of science. Came out in a paperback, saw it in the bookshop, thought, never heard of it before, but thought that looked interesting. And yeah, that probably is, yes, it was interesting, and it's probably, fated me to do for the next 30 years. But basically what he's looking at is the mathematics and physics of things, particularly almost like what constrains growth. The things almost like the things that grow can't go against physics or have to almost like work with it, and things that work iteratively on top of each other. So like the shapes of shells, where at each early stage it needs to be a viable seashell, and then as it grows, it sort of adds another chamber, adds another chamber, adds another chamber. We're working with things like the shapes from surface tension. How particularly, one thing I really get from Darcy Thompson is how constraint, almost like you don't have freedom to design anything. There's actually lots of constraints. You're actually working with, almost like deliberately with constraint when you actually got a growing structure. And these sort of amazingly beautiful mathematical patterns that are created by growing organisms. And thirdly, Ernst Haeckel, who's a zoologist and philosopher from Germany, and did these amazing sort of studies of natural forms, where he's particularly interested in things like symmetries and asymmetries and familiarities between common things between maybe very different organisms and at very different scales, but often having very similar patterns and forms. And did these sort of like beautiful studies, often, I believe he's actually slightly faked things occasionally, but often with these very sort of almost manipulated systems, like emphasize the things like the symmetries in the structures. And also, to be honest, I think there's a beautiful simplicity about how he represented things, which is, I mean, a lot of the way I try to present work, to be honest, it's a pretty direct, almost like homage to Haeckel's, almost like, I think, simplicity of presentation. So I'm going to mostly focus on this short talk today on this more recent work, this sort of cellular-based growth work. We're just going to talk very briefly about some earlier growth-based work that I did about 10 years ago, which was a series called Aggregate, which is basically based on variations on a quite classic computer algorithm called diffusion-limited aggregation, which is basically almost like the simplest system for growth I can imagine. It's basically growth by deposition. So you take a structure, and then you just like let things like float around until it hits that structure and you deposit it. And you keep on letting these things float around till Walker particles deposit on this surface. And just by, it's this astonishingly simple rule, you end up building these amazingly complicated sort of filigree structures. And what I was looking within the aggregation series was almost like exploring things like biasing the system. Almost like if you then, these particles, they move around, if you bias it, almost like changing the environmental rules they're growing in. So it's almost like, imagine like a coral growing in water. If the water's very, very still, it's like a pool without any tides, it might grow one way. Where if there's quite strong tidal flow, then it might actually grow into some really quite different sort of structures. So it's sort of looking at those sort of things, almost like sort of taking this very simple algorithm, changing environmental rules, and then seeing what biases, how they affected the sort of structures. And what it produces is, say, quite an amazing range of different, very interesting structures and forms. But with like two limitations as far as I'm concerned. Everything tends to be coral cum fern-like. And they're fundamentally static structures, because you're basically repeatedly depositing. You can animate things like this structure growing up over time, but the structure itself is a static one. And so I was thinking almost like, well, what's different when you see other things you see in nature, particularly more animal things, like, internal organs, brains, lungs, folded skin, things like bark on trees and things, and fish scales and stuff. What's different about those? And almost could you create a system which almost like, I know this produces some really quite interesting behavior, but could I make a system which is more general and hopefully could actually get into some of those other sorts of structures you see in nature? So that was very much the thought behind developing what's called the cellular forms. So what the idea was, fundamentally, is almost like instead of depositing things on the outside, have cells growing on the inside. So have internal organs grow by like cellular growth of cells deep in the structure, potentially splitting. But what I'm trying to come up with is a system which, in almost like one extreme of the system, would basically be equivalent to diffusion-limited aggregation. So, because I know that can produce rich results. So the idea is this, almost like if an extreme of the system, it could do DLA, but could also do hopefully other things where I've got cells which are splitting in these sheets of splitting cells, and I've got forces between the cells. Hopefully what I'm going to end up is dynamic, changing, moving structures rather than static ones. But if I almost like one extreme of the rules where there's almost no forces between the cells, so it's static, and the cells that grow are just grown by the things coming in from the outside, hitting a cell, that cell grows, basically I've got diffusion-limited aggregation. So the idea was, so you see, was like, I know that's rich, but if I can produce a wider space of possibility, hopefully that's going to produce, hopefully, you sort of definitely hope it's going to produce even more interesting, crazy things. So very briefly, I've actually got a paper online if you want to go into the details and things. But very basically, the idea is that actually all the structures are basically made out of sheets. So I've got this sheet of cells, and then what happens is, well, I can use this thing, can't I? Have a go. So, and then basically, cells accumulate food. And when the cell accumulates enough food, it can split. So there can be rules in there for how is food created. Does food pass from one cell to another cell and things like that? Typically what I do is that food's created by light coming in from outside, and when light hits a cell, it basically it's like photosynthesis, it creates a bit of food. But that cell can then share the food if it wants, so it can be greedy and gobble the food itself, or could share the food with the cells around it. So you can almost be like a cardiovascular, sort of transport food from one cell to another. And when you pick a cell to be grown, it's basically almost like what you do is so I pick this cell to split and grow, then I almost like choose a pair of links to break, almost like where to break sort of plane of cleavage, almost like which direction to split in. Delete all the connections that one side of those links, create this new cell, push the two cells a bit apart, and then reconnect the daughter cell back up to the neighbors. So basically, I start with a sheet of cells, and then I'm going to end up with a new sheet of cells, just with an extra cell sort of inserted into it. Then, let's see whether this works. Yay, it does work. So basically it says, that's the wrong way. Cell division. Okay, then there's forces between these cells. So if you look at the paper, you'll get more details about these, but basically the things like the springs, one cell pushing the other cells around it. Also a force which tends to make the cells bulge outwards, so that if the surface is sort of squeezed, it tends to almost like make the surface want to fold, want to bulge. And another force is almost like doing the opposite. It's trying to say, what I want to do is flatten the surface, so that if there's a bulge, try to flatten it out. And you can sort of see maybe that, almost like depending on the relative strength of this tendency to bulge and tendency to flatten, hopefully I'm going to produce like complex sets of different behaviors of maybe some surfaces that fold like mad into all sorts of wrinkles, and other surfaces that almost want to stay as flat as they possibly can. And one thing I was really trying to almost like emphasize in this was trying to create sheets which naturally would want to fold. I mean, like in mathematics, there's like this idea of surface curvature, and things like a surface that has positive curvature will tend to, which way around is it? Well, curvature one way is basically things that it just folds up into spheres. But if you have negative curvature, it will tend to want to wrinkle. There's actually a beautiful book on, it's called like crocheting adventures in hyperbolic surfaces, or something like that. It's just beautiful about how to knit shapes of things which naturally want to wrinkle into all sorts of shapes that look like, these sort of shapes of complex sort of flower petals and things like that. There's just a natural tendency. If you have a surface where you almost like put extra links in, it will just naturally want to fold into really, really hopefully interesting complex shapes. And the final force we're having this is actually some of the most important ones, and this is a bit Darcy-Thompson-like. Basically, an extra constraint in there. But basically what I found is that if you just then set the system up like that and then just let it go, you'll basically produce junk like this. So there's cells growing, splitting, and basically it's folding in on itself, and every cell's going through the other cells, and you're ending up with just an unstructured ball of nothing. If you actually put a little repulsion between the cells, so it's almost like there's a little electrical force in each cell which pushes the other cells which are nearby away from it, suddenly you get this really, or potentially can get these real, so it's exactly the same setup between these two, exactly the same parameters, but just little electrical static repulsion between cells. Suddenly you're getting these coherent, meaningful structures. Because it's sort of like there's this tendency just for it to, cells push themselves apart from each other rather than folding in this almost like crazy sort of plastic bag. And that was one of the critical things, just almost like inject that, put that in just the right amount, and suddenly interesting shapes. So I'm going to do some implementation, but I wrote the code in C++ and CUDA, basically almost everything. CUDA is basically a language to make use of the graphics card in computers. So it's one of these computer gamers who thankfully have made ridiculously powerful computers amazingly cheap. So basically you've got supercomputer power basically in a card which, okay, it's probably got some very dodgy graphic art on it because it's aimed at computer gamers, but it's an amazingly sort of powerful computing device. So basically I'm written in CUDA for processing these simulations. One of the things I'm really interested in is trying to push the limits of detail and complexity. I have background in visual effects and animation, as John said, and one of my rules of thumb was almost, unless you can do at least 1 million of something, and hopefully tens or hundreds of millions of things, you never get to an interesting level of complexity. So as my sort of line in the sand was like, unless I can get to at least about 10 million, not interested. And that's one of the main reasons CUDA's it's not a language you would use by choice unless you have to, probably. But it means that you potentially got, like a modern graphics card can have over 3,000 processors, all potentially computing all this stuff in parallel. So the sort of things are produced. First one of this is almost like a coral thing, a bit like the sort of things you got for diffusion, limited aggregation, a bit sort of like the aggregation series. But also, these almost like more brains, like almost more folded skin, even more sort of stream, quite reptilian sort of skin. It starts, there's only a few points in this space, but you start getting, I think these really, I like these. You leave the computer crunching overnight for weeks, and you sit every morning, you have a look at it, and 99 times out of 100, it's just not, I haven't produced anything at all interesting. And then once in a blue moon, it produces something like, okay. Particularly when it's just, each cell is only influencing the cells immediately around it. There's no global structure, no global forces. I haven't been painting texture maps, stretch it in this direction more than that direction, or produce folds. It's all, no rabbits up my sleeves. It really is genuinely coming from these equations, interactions between cells, just influencing their immediate neighbors. And I think that's one of the things that's interesting. It's almost like how simple these rules can be, yet produce what looks like really almost like structured organic sort of complexity. Actually, I've got no idea what produced this, but this is probably one of the least biological things that's been produced by it. Which actually goes out to one of the fundamentally interesting things, that this is if there's an academic discipline that I'm close to, it's probably more close to the artificial life. Though this is an incredibly unbiological system, almost everything it creates is in some way reminiscent of things in nature. Like it looks a bit like, you look at shark scales under microscopes, they almost look like these. Brain, lung, internal organ, I think it's definitely onto the ugly rather than the beautiful, but there's something maybe quite evocative about this. Almost everything it produced, a system produced that I've found that's interesting, is at least deeply reminiscent of things that we're used to. So I guess that raises ideas of, if we went to an alien planet and things were growing on it, I think that everything would look deeply familiar. It might be a totally non-DNA based, totally different biology, but growth itself, I think, produces remarkably familiar sort of structures. This also looks at different renderings. This is almost like the same structure, so that's the outside, and then like that, this is the inside. It's almost like an X-ray looking into it. I've got actually a short animation. So this is, what I quite like this is almost like this, you see that this is looking into the structure, and there's some things you don't see really from looking at the internals, which you see on the outside, like these waves of, growth going across the surfaces. Again, that purely comes from simulation. It looks actually like someone who showed me like frog embryos growing. They actually have remarkably similar sort of waves of growth. There's also things happening on the inside, like this growth of this, I guess what biologists probably call a vacuole or something like that, happening, which is, if you just saw the outside image, you'd have no idea of these things going on in internal structures. Again, just coming purely emergently from the rules. Now I'm going to talk about two different sort of variations on this system. So all those things I showed you so far, there's these growth rules, but things like, there's no biases to particular directions. It's like generally things are growing because cells receive light, but the light comes from all directions uniformly. This was like a diffuse light that completely envelops the cells. And everything sort of ends up as all spheres in the end. Spheres with hopefully really interesting detailed surfaces, but generally sort of ball-like sort of structures. Now, this was just an experiment in just one small change to the system, just that the light comes from on top rather than the light comes from all directions around. Nothing else changed in the system at all. And what that basically almost like instantly produces very plant-like, can produce very plant or fungal-like sort of things. So this is forms growing, and basically you see they grow upward because light's coming from above. The cells that receive the light get the food, and basically if those cells are greedy so that they swallow the food themselves, only the cells towards the top grows, and we add all the branching, and there's lots of things like L systems and things like that are conventional ways of creating plant-like things where you've directly programmed, when to branch and things. There's no direct code in there saying produce this branch, now fork, now do this. All the branching behavior, everything like that is, again, emergently just coming from rules at the cellular sort of level. And then one thing, actually, if you go to Waterman's, I've got one of the things in there is actually a set of 4 different screens. And one of the screens shows almost like the areas where light's hitting. And another of the screens shows the areas of new growth. And what you start seeing is these more fungal structures are basically where the cells are sharing food into the structure. So it means that the other cells down below are still growing because they're almost, even though they're in shadow, they're not seeing any of the light, they're still getting food because the cells which are getting the light are being cooperative or sort of sharing the food downwards. So you get this sort of less plant-like things where you have more sort of food sharing going on. This is now another slight change to the system. So this is what we call hybrid form. So whereas all those previous things, it's like, yeah, not too badly. All the previous structures, all the cells are fairly the same. There's only like one set of parameters. There's nothing that changes the simulation as it goes into it, which is actually one of the things that some of the people from the artificial life community are particularly interested in these simulations, that it looks like almost that they go through various phases of growth. There's nothing that almost has like timed chemicals saying, at this point, start doing this, at this point in time, doing this. It's basically just one setting of parameters. All the cells are identical to each other. They all sort of like, like that. And these is almost like the first steps into the smallest amount of cell differentiation, basically having 2 different cell types in the structures. And then, so basically on starting the ball, and the blue is one cell type, the green is another cell type, and then the cell between almost like a blend of properties between the 2. And then as it splits, so almost like the blue cells here, you can see almost like tend to produce tendril things, whereas the green cells maybe produce like bloom-like things. And the cells between it produce something between the 2. So you almost end up with a range of different structures in the surface, which almost start competing with each other for sort of space in the form. So ludicrously simple model of cell differentiation, but actually it produces some really quite interesting variety of structures. And another thing I've been doing is exploring a bit like saying just like the X-ray and external views. Because I've been doing this is exploring some other ways of visualizing. So like this one was like visualizing the areas of new growth. So basically I'm flashing a cell with bright blue when it splits, and then it sort of like fades back out to black, so it's based on the age of the cells. And you end up with these actually really quite interesting, almost like electrical patterns of activity of showing like the areas of growth on the structures. Again, it's like I haven't injected in texture maps or anything like that to grow it, to drive it. It's just that was what comes naturally from the simulations. And then this visualization is just showing like different cell types. X-rays and external views again. So I'm actually going to show you, so one of the things I've been doing is showing multiple views of the same simulations, effectively. So I'm just going to play you one example, which is just from the, it's like X-ray-like structures. We have some sound for this. So there's basically 4 different camera views of the same simulation grower. And what you start seeing, hopefully, is some really surprisingly biological things. These are basically effectively just like bags of springs, but tweaked. If you just get the almost like parameters, forces and track one bag of growing springs, I guess is a really critical thing. So that there's it's growing over time. But really simple interactions produce remarkably complicated structures and forms. Actually, a techno DJ producer producing this because this is not real simple techno. Producer has a PhD in genetics, so yeah, it's strange. I think we would get on very well. two together. Quite defined structure. So all of these almost end up within one cell type, just almost like totally dominating by the end. So it's okay, so a couple of some exhibitions had. So this is actually from the last town. Why? So this is from last year's European Conference in Artificial Life. That actually gave me access to what's called 360 room at York University. So it was like a two-story high-def projection onto four walls of a room. It's also got 36.4 surround sound as well, sound system. These are those, it was like 4 images you're seeing there, projection or walls that we had at the ECAL conference. This is actually from Waterman's. At present, there is an exhibition just opened last week, running until the 21st of July over at Waterman's near Kew Bridge. So this is an exhibition with prints. This is a 3D printed sort of cellular form. There's a little holographic display in there. There's all sorts of different. I'm exploring different presentation methods, almost like what the strengths and weaknesses are of trying to present almost like the original things almost just this data in the computer. But then how can you actually make that into something visual, perceivable? And here's actually one of the things was like it was like slightly hidden stuff in there's this central sort of installation with these 2 screens. Some mirrors in there, and I was intrigued to see if you can work out what's actually going on in there. There's some little hidden things to find. So yeah, obviously I'm prejudiced, but I hardly recommend making the trip over to West London to have a look at the exhibition. It's probably the most complete exhibition I've put together so far. Future work, obviously there's lots of different directions this could go in. It's almost like some experimental set up for, you could try an experiment in all sorts of different ways. So the thing I'm interested in is particularly things like, more complex interactions between cells, where maybe cells mutually sort of inhibit and promote each other. Cell death rather than cell growth. At present, all cells just grow. What happens if you have reasons why cells die? What happens when a cell dies? Does it create a hole in the surface, or does the surface heal back up? If it heals back up, how does it heal back up? All these sorts of things could hopefully produce more interesting variety. 3D printing, robotic manufacture, I'm already sort of started getting into. That's already one of my reasons for currently doing the things with the Bartlett. So they've got a very interesting robotic manufacturing lab there. And also one of the big things I'm also working for quite a while was like backstory. Maybe this is a completely another talk I could do, but there's a lot of work I've been doing on how do you explore these spaces? How do you try to work with this sort of space of, there's a very few places in it that it does some interesting things. How do you find that? Particularly if you're almost like wanting to creatively influence it, but not overly control it. I don't want to design the final thing. I want to explore what it can do, but how can you actually sort of do that? So just a quick thanks to Max Cooper, who's the musician I've been working with for a few years now. Who do basically much all the music and the things I've been working on. It's almost like I do things, graphics for him, I've done a couple of music videos for him, and he's been doing things for me for exhibitions and things. The Foundry, where I used to work and still allowed to use their software, which for just editing things like that's great. And NVIDIA, who over the years have given me a few of these graphics cards, which is, that allows me to actually compute these crazy amounts of things, even though what I've got is actually now my computer and my wife's computer up in the attic, but by having gamer-level quality cards, you can actually do surprising things in computers nowadays. That's it. So that's my email address. Do we have any time for questions?
We do, yeah. Just hold on for the mic, please. Hold on for the mic.
I did waffle a bit, I'm afraid.
It's fine. I got mesmerised and I lost track of time.
I have two questions, really literally. One about the roots a little bit more, because the name that everybody associates with when cellular automata really took off is John Conway.
Yeah.
The great genius and total eccentric.
Mm-hmm.
Say a little bit about...
Used to be one of my lecturers, actually, many years ago.
Wow, well, there you go. A little bit more about him. And then the other thing that crosses my mind is, if these organisms are given senses, this relates to deep learning then.
Yeah.
And that your work has potential enormous application, not as an art form, but as a way of starting to think about all the enormous explosion in AI that's going on at the moment. So those are the two subjects that are fascinating.
So I guess, everything could be defined in different ways and things like that. I guess I see this less as cellular automata. Cellular automata don't have to be, they're usually like on a regular grid, in a very simple, just like, you're surrounded by 5 cells, live, die, That always what cellular automata revel in particularly the game of life, is, astonishing simplicity, but it's not trying to be a growth system. It's trying to be almost like a complexity system. Obviously it's almost like a continuous version of a cellular automata is one way of looking at this, but I guess it's less how I think about it. If you could analyze it more like Stephen Wolfram style, as if you wanted to. I think John Conway does astonishing work. As I was a lecturer, but actually not in dynamical systems. I was a lecturer on mathematical logic when I was actually an undergraduate. So it's more genuinely the Darcy Thompson, Alan Turing, reaction diffusion. And I guess when I was an undergraduate, the area of maths that I most specialized in was dynamical systems. So I must say functions that feed back into themselves and have the possibility of very complex behavior. So that's probably the mental model that I've more got in mind. I'm actually very interested in machine learning, deep learning, things like that. That's one of the reasons I'm actually on a sabbatical at present to try to spend time learning a few of the many things which I've been wanting to do but haven't had time to do. So almost like deliberately gave up the day and been doing things like, learning about deep learning and stuff. I'm probably more looking at actually things to how to search the space, that actually won't get into the details because I'd probably go on for ages about it, but the Species Explorer, the software that I've been writing to explore these spaces, is actually a sort of hybrid combination of evolutionary search techniques and machine learning techniques, though generally more what's called lazy machine learning rather than deep learning, or like deep neural networks, things like that. But I'm very interested in them as particularly ways of almost like further assisting that search of the space. I'm also interested in with like cells stimulating adjacent cells in more complex ways that could be almost like rhythmogenesis, so almost like cells triggering motion in the cells, and maybe more like Stuart Kauffman's what's called K networks. Of almost like which is more towards cellular automata. It's almost like excitation of one cell to the next. So it's almost like almost very simple neural model, but actually in the cells. So yeah, there's so many different ways you can go in this. Yeah, I've studied the richness and complexity that comes from K networks. I think random K networks, I think, is really interesting.
Andy, you gave such detailed answers. I'm afraid we really ought to move on.
Okay.
So it's a real shame, because I had a load of questions for you too, and this lady over there did too. But we can talk over a drink when we take a break, and we have time at the end. 15 minutes or so if you want to come back and speak to Andy.
Okay.
So thank you very much, Andy, for a very, very interesting talk.